When we last met, our vodcast was about dissociation in the process of solvation. And you can have water take something like salt and split it up into its ions. And that's simply called dissociation or splitting apart. The process of surrounding a solute with solvent is called the process of solvation. And there are several factors that can influence the rate of solvation. For example, agitation or stirring. Obviously, anything that can increase the collisions between a solute and a solvent will increase the rate at which the solute dissolves. Quick detour: solute is the thing being dissolved, solvent is the substance doing the dissolving. Many of our examples show a solid solute being dissolved in a liquid solvent, but it doesn't always have to be that way. So here's someone making the ingredients of, I don't know what, carrot cake, dissolving in each other by agitation, stirring. Another way to increase the collisions between a solute and a solvent is to increase the surface area, and that can be done by something as simple as grinding a chemical in this mortar and pestle. A third factor is pretty obvious: the factor of temperature. When you increase the kinetic energy by increasing the temperature, you are creating more collisions between solute and solvent again, and so it makes it easy, for example, to dissolve the sugar into the hot water to make syrup. Now, when we measure solubility, what we're measuring is how much solute can dissolve in a given amount of solvent. Usually it's expressed as a certain amount of solute that can dissolve in a particular amount of solvent at a specific temperature. So for example, we need to say not only can 36 grams of solid salt dissolve in 100 grams of water, you have to say at what temperature. Because as the solubility curve is that we're going to examine in just a moment, substances' solubility are highly dependent upon temperature. These are examples of solubility curves. The solid lines represent solid substances. And for all solid substances, except for a few like the cerium salts, if you warm them up, they're going to become more soluble in their solvent. Notice that this is the common way that you will see. We often express water as the solvent for various substances, since it's the universal solvent, and we express it per 100 grams. So if I was to read this graph, for example, I might pick somebody like, I don't know, ammonium chloride. And what the graph is saying is that at 70 degrees, I cruise up and touch this line, and then I kind of hang a left. Approximately 60 grams of ammonium chloride would be soluble in 100 grams of water. If I had 200 grams of water, that means twice that amount, or 120 grams, could dissolve. So pay attention on worksheet problems as to the amount of water that's being provided as the solvent. You should also notice that the dotted lines, which represent gases, are decreasing in solubility as temperature increases. That makes sense because if I increase the kinetic energy of gas molecules within a liquid, more of them will have sufficient kinetic energy to break free and go out into the atmosphere above the liquid in which they've been previously dissolved. So that's a solubility curve, and you'll have a worksheet to complete about that. Now, solubility can also be described with three different terms. The first term is really easy to understand. Unsaturated solutions look clear. You might want to jot that down on your notes. And that's because the amount of solute that's dissolved is much less than the maximum allowable at that particular temperature. So if I just have a few ions of sodium and chloride dissolved in a certain amount of water, and if that water had more dissolving ability, more room to dissolve more ions, it'll still look clear, a homogeneous solution, and it is what we call unsaturated. However, if you start to really pack in the salt, so much so that now you have saturated it, what you will see is you've gone beyond the maximum dissolving ability of that amount of water, and at a certain point you can't dissolve any more solute into that solvent. If it's a solid that's in a liquid, what you will see is at the bottom of the container some solid solute would be present. And that's how you know a solution is saturated. It'll have a solid solute present at the bottom. And it's important to understand that even though it doesn't show it, the salt continues to dissolve at the same rate that sodium and chloride ions get back together to make solid salt. But they reach an equilibrium at which the two rates are equal to each other, so it appears nothing is happening, but actually there is. So to repeat, a saturated solution, lots of ions or molecules dissolved with solid solute present at the bottom. Now the last example is a little hard to describe without watching a video and actually the demonstration that we will be presenting about supersaturated solution. A supersaturated solution is weird. It looks clear. Write that one down too. But actually, with careful heating and stirring and cooling over a long period of time, you can get more solid solute to go into solution that would be predicted for that temperature. The thing is, they're unstable. And if you jiggle that container, or if you add a seed crystal, as you will see in our demonstration and the video, they can't hold on to that excess solid and will suddenly come out of solution, and you'll see a solid crystallizing out of the supersaturated solution. But until you bump them, they look clear, and you couldn't tell the difference between them and an unsaturated solution unless you had actually prepared it. So let's take a look at a little video that shows a supersaturated solution at work. And I think I've got enough of the screen here. Let's take a moment to watch this guy.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added. Here is the process again in slow motion.
So as you can see, the seed crystal instantly makes the unstable solution come out of solution, and there's the maximum, over the maximum amount of solute coming out of solution in this instant reaction. It's also very hot too. So that is a supersaturated solution. Let's go back to the PowerPoint then and pick up on that concept. So one of the special ways that we can use this process of supersaturation is when we make fudge. Here's all the ingredients you would need to make fudge. And what you need to do is to mix it by heating and stirring it to get as much sugar to go into solution as possible. And to do so, it helps if you use a copper pot, because that helps dissipate the heat, and you do this over a long period of time. Then what you need to do is to cool the fudge very, very slowly. If you cool it too fast, the supersaturated sugar solution will come back out and it won't work. But if you cool it slowly on a marble slab like you see here, you'll be able to keep that supersaturated solution supersaturated. Here they're stirring what looks like divinity fudge. Then, as you line up your fudge in whatever kind of shape you need to cut it, you can add nuts and goodies as it cools. And then, of course, slice, eat it, and enjoy. But the way you know that you didn't have a supersaturated solution of fudge is because on your tongue, the texture of the fudge is kind of gritty. You let it cool too fast, and so the supersaturated solution came out of solution instead of feeling creamy and smooth if you had let it cool more slowly. That's probably a good stopping point for us to pick up until the next podcast.